Welcome to this lesson on upper and lower bounds. By the end of this video, you'll be able to identify the limits of accuracy for rounded data and calculate the bounds for perimeters and areas in geometric problems. When we measure something, like the length of a desk or the weight of an apple, our measurement is rarely exact. It is usually rounded to a certain degree of accuracy, like the nearest centimeter or the nearest gram. Consider a ruler measuring a line. Often, the end of the line falls between two marks, like 7 and 8 centimeters. Because of this rounding, the true value could actually be slightly smaller or slightly larger than the recorded value. We call these the lower bound and the upper bound. Let's start by defining what these bounds actually represent. The lower bound is the smallest value that would round up to our given number. The upper bound is the smallest value that would round to the next unit up. To find the bounds, take the degree of accuracy and divide it by 2. Then add and subtract this value from your measurement. For example, if a length is given as 8 centimeters, measured to the nearest centimeter, our degree of accuracy is 1 centimeter. Dividing this by 2 gives us 0.5. Subtracting 0.5 gives a lower bound of 7.5, and adding 0.5 gives an upper bound of 8.5. Notice that any number from 7.5 up to, but not including, 8.5 would round to 8. In IGCSE exams, we use 8.5 as the upper bound, even though 8.5 itself usually rounds up to 9. We treat it as the limit of the values. Let's look at another example with a different degree of accuracy, as this is a common place where students lose marks. Suppose the mass of a parcel is 4.7 kilograms, measured correct to 1 decimal place, or the nearest 0.1 kilograms. Our degree of accuracy here is 0.1 kilograms. Following our rule, we divide 0.1 by 2 to get 0.05. So, the lower bound is 4.65 kilograms and the upper bound is 4.75 kilograms. We can write this as an inequality. The mass is greater than or equal to 4.65, but strictly less than 4.75. Take a moment to think. If the accuracy was to the nearest 10 kilograms, what would we divide by 2? That is right, we would add and subtract 5. Now, let's apply this to calculations, starting with the perimeter of a rectangle. This is a classic IGCSE exam-style question. Consider this rectangle with a measured length of 12 and a width of 7. First, we must find the bounds for each dimension individually. For the length of 12 centimeters to the nearest centimeter, the lower bound is 11.5 and the upper bound is 12.5. Similarly, for the width of 7 centimeters, the lower bound is 6.5 and the upper bound is 7.5. To find the lower bound of the perimeter, we use the smallest possible values for both length and width. The lower bound of the perimeter is 2 times 11.5 plus 6.5, which gives us 2 times 18 or 36 centimeters. Similarly, for the upper bound of the perimeter, we use the largest possible values. This gives us 2 times 12.5 plus 7.5, which is 2 times 20, resulting in 40 centimeters. So, while the calculated perimeter is 38 centimeters, the actual perimeter could be anywhere between 36 and 40 centimeters. Next, let's look at calculating bounds for the area of a rectangle. This involves multiplication, and the principle remains the same. We want to find the absolute minimum and maximum possible results. Consider this problem. A rectangular field has length 80 meters and width 50 meters, both correct to the nearest 5 meters. Calculate the upper bound for the area of the field. Notice the degree of accuracy here is the nearest 5 meters. This is a common trap in exam questions. We divide 5 by 2 to get 2.5 meters. This is the value we add and subtract. For the length of 80 meters, the lower bound is 72.7.5 and the upper bound is 82.5. For the width of 50 meters, the lower bound is 47.5 and the upper bound is 52.5. The area is found by multiplying length and width. To find the upper bound of the area, we multiply the two upper bounds together. The upper bound for the area is 4,331.25 square meters. If we needed the lower bound, we would multiply the minimums, giving us 3,681.25 square meters. Notice how a small rounding difference in the measurements leads to a very large range in the possible area. To wrap up, let's review the key steps we have covered today. First, identify the degree of accuracy. Second, divide that accuracy by 2. Third, add and subtract to find the lower and upper bounds. And finally, for perimeter and area, use the appropriate bounds in your formula. We have successfully met our objectives. You can now identify the limits of accuracy for any given measurement by finding its lower and upper bounds. You also know how to calculate bounds for perimeter and area. You also know how to apply these bounds to geometric problems involving addition and multiplication. When dealing with perimeters, you add the bounds. When dealing with areas, you multiply them. Remember to always check the degree of accuracy carefully, as it's not always to the nearest whole number. In your next study session, you might want to explore how bounds work with division and subtraction, as those operations require a slightly different strategy to find the maximum and minimum outcomes. Keep practicing with past paper questions to build your confidence. Well done on completing this lesson.